good evening, good morning, everyone. We are very proud to have Gabriele as a speaker of the GGI Tea Breaks colloquia, not only for his scientific weight that we all know, and we are all eager to hear about his reflections on 50 plus years of success stories, but also because he contributed a lot to the success of the GGI. He has been the chair of the advisory committee, which was nominated to advise about scientific and management structures of the Institute. He followed all the GGI activities from the very beginning, but also he has been part of the selection committee of the Galileo Galilei Medal, a prestigious award established by the INFN and GGI and assigned every 2 years to scientists who have achieved outstanding results on the areas of theoretical physics. Last but not least, Gabriele has been one of the organizers of the last long-term workshop, the GGI, on gravitational scattering in spiral and radiation, which was run online. Despite the obvious difficulties due to the online format, the workshop, together with the related training week and conference, were a success, and the online discussions were really exciting. You can have a look on our YouTube channel. All this thanks to the efforts of the organizers and of Gabriele in primis. So really many thanks to him, but now I do not want to take more time, and I leave Alessandro to introduce the colloquium. Thank you.
Thank you very much, Stefania. And as you said, it's a particular pleasure and honor to have Gabriele as a speaker today. I don't want to add much to the very nice introduction that you did for him, also because indeed he needs no introduction. There is a very long list of awards that he received in his very long and distinguished career. I don't want to recite it. You can always look it up. And his contributions and his work, his scientific work, really speaks for himself. So instead, I will very shortly give him just the floor to tell us about his reflections on 50 plus years of success stories and on some puzzles, as I said in his abstract. Before that, just a little bit of housekeeping. I would ask the audience if they have some questions during the talk, maybe they can write it in the chat. If it's an urgent question, something that really needs clarification. And otherwise, I would ask you to please reserve your questions for the end of the talk, because at the end of the talk, we will have time for discussions. And also in that case, I would ask you to either raise your hand so that we can unmute you and give you the word, or write your question in the chat so that we can sort of proceed in an orderly way, since I think we are a very large number. I see that we are almost 200 people already now. Okay, without any further ado, please, Gabriele, take it away.
Yes, thank you, Alessandro, and thank you, Stefania, for the nice introduction and for this invitation. And hello, everybody, morning, afternoon, evening, wherever you are. So I'm going to tell you about some thoughts of mine following more than 50 years of success stories. In this first slide, you see 3 recent examples, the LHC, PLANCK experiment, and the LIGO and VIRGO experiment. But let me start with a little, okay, it worked until now, and now I cannot scroll. Yeah, okay. With a little preamble, I graduated in 1967, and therefore I have been very lucky of having lived and worked through what we can call an exceptional era in the history of fundamental physics. And looking back at more than 50 years spent on this fantastic adventure, I would like to share with you some personal thoughts. This will not be for experts. I apologize in advance to the experts for those remarks that will be too trivial and or old-fashioned. On the other hand, I'm an old guy, so I hope you excuse me. But if the remaining thoughts don't make much sense, please let me know, either right away after the talk or later if you prefer. So this is basically the outline. I will start by recalling you what is the standard model of nature today. Then I will stress the role of quantum mechanics, both for elementary particle physics and for gravity and cosmology. I will stress the role of symmetries of various kinds. Then I will discuss quantum corrections of various kinds. In fact, in particular, some I call the good and some the bad. Then I will advertise that we need an IUVC, and the acronym will be explained later. And we'll ask whether quantum string theory can be that sought after object. And I will finally, after mentioning some miracles in quantum string theory and some less welcome ones, I will summarize the talk. So the standard model of nature, say after the recent successes of LHC, PLANCK, LIGO, and VIRGO, as you know, consists of two parts. There is a standard model of elementary particles and their non-gravitational interactions, which is based on a gauge theory. And then there is a standard model of gravity and cosmology based on general relativity. Now, throughout more than 5 decades, this standard model of nature has been tested thoroughly and only needed slight amendments or extensions. And in my opinion, it represents an unprecedented triumph of reductionism. If you want, in one sentence, the theory of all known, and I underline known because this is not probably the full set, known particles and forces can be written on one single slide, which is here. So the standard model of nature, as I said, consists of two pieces, the standard model of gravity and the standard model of particle physics, which has to be made generally covariant in order to marry it with general relativity. Now, in the first two lines of the slide, you see first the famous Einstein-Hilbert Lagrangian or action. And recently, we may need to add to it a so-called cosmological constant term, which, by the way, was introduced already by Einstein, although for the wrong reasons, in 1917, so soon after the invention of general relativity. In the following 4 lines, you see the standard model of particle physics, which consists of a gauge interaction terms, which is very much fixed by gauge invariance. Then the so-called Yukawa coupling term in the Lagrangian, the Higgs interaction, mass and self-interaction, which is on the way of being confirmed by the LHC experiments. And finally, again, some novelty, the need to give mass to neutrinos. And this is just an example, if you like, the so-called seesaw mechanism, a way to give mass to the neutrinos. Now, going a little bit more in the details for the standard model of elementary particles, I remind you that this is a quantum relativistic theory, which is also known as quantum field theory. And it's important that the quantum and relativistic nature of this model manifests itself not only through real, but also through virtual particle production. And these are essential for the agreement between theory and experiments. I remind you that if you neglect this, in particular the virtual particle production effects, the theory is off with respect to experiments by many, many standard deviations. And actually, the virtual effects anticipated the experimental discoveries of both the top quark and of the Higgs boson. And according to many, the absence also of low-scale supersymmetry could already be guessed in the absence of virtual effects. So this is just to illustrate the point I just made. This was the situation at the end of the LEP era at CERN, where you see on the right a plot of the Higgs mass versus the goodness of the fit to the data. The yellow region is the region which was excluded already by direct search of the Higgs boson at LEP. But as you see, the chi-square goes up very rapidly if one goes much higher than the 100 GeV scale. And therefore, the clear prediction was that the Higgs boson had to be not far above that threshold. Turning to the standard model of gravity, which is general relativity, that is a classical theory which incorporates the equivalence principle through general covariance. And the equivalence principle means the universality of free fall, Galileo's famous idea. And this is tested with incredible precision with experiments like STEP, which reach precisions, I forgot exactly, but 10 to the minus 18, I think, something of that order. Also, the deviations from Newtonian gravity implied by general relativity are well tested. Furthermore, general relativity makes new predictions like the existence of black holes and of gravitational waves. And there is, by now, overwhelming evidence and even new evidence through gravitational waves of the existence of black holes. And for gravitational waves, there have been for quite a long time indirect evidence, and now, after LIGO and VIRGO, even direct evidence. This was, for instance, the evidence for the emission of gravitational waves from pulsar binaries as a function of the two masses of the binary system, and to the extent that these different curves meet in some region, this represents a confirmation of the theory. So the existence of gravitational wave was quite clear already from these indirect indications, but then, of course, the beautiful experiments with interferometers confirmed precisely the existence of gravitational waves as predicted by general relativity, both numerically and analytically. And maybe I take the opportunity to say that the Galileo Medal this year has been awarded for theoretical work precisely on this subject. Now, however, you could say that while for the standard model of elementary particles, quantum mechanics is crucial, as I stressed, it looks as if classical general relativity can cope already with gravity without the help of quantum mechanics. However, I claim that things change a lot when we consider cosmology, the applications of gravity to cosmology. And the reason can be seen in the so-called concordance model of cosmology. In fact, since a few decades, say since the 80s, we have a good, we can call it standard cosmological model, which combines the inflationary paradigm with that of a dark sector in the energy budget of the universe. And I remind you that without inflation, we would need a huge fine-tuning of the properties of the hot Big Bang. This is the so-called cosmic concordance, namely different experiments like CMB experiments, the Hubble diagram of supernovae, the theory of structure formation. They all converge to give a certain value, optimal value for the density of matter and for the vacuum energy density. So, and this in particular are the data from the Planck power spectrum showing how well an inflationary model, which has a few parameters, but how well it fits the CMB data, in particular these acoustic peaks. So from that you find out that the cosmic pie of the universe consists of these three different components, out of which only some 5% is really ordinary matter. Now, I should mention right away that there is now a tension which has not disappeared in spite of improved experiments on the value of the Hubble parameter H0, and this could be really an alert for some new physics, either in particle physics or in gravity. Now, the reflection R1, which is reflection number 1, is that modern cosmology needs quantum mechanics. And there are two reasons I would like to advocate. One is the origin of structure. If you take inflation, but without quantum mechanics, then that scenario produces a perfectly homogeneous universe. Why? Because possible initial inhomogeneities are completely erased. If you want, they are stretched outside our present horizon. But then the universe becomes so smooth, so homogeneous, that there is no mechanism to form the structure we see in the sky. With quantum mechanics, the situation changes drastically. The classical initial inhomogeneities are still erased, precisely like in a classical theory. However, they are replaced by calculable quantum fluctuations, which are produced, amplified, and stretched throughout the inflationary epoch. Throughout is the crucial thing, namely, you cannot turn off quantum mechanics, so all throughout the inflationary epoch, quantum mechanics keeps producing fluctuations. And the beautiful thing is that the cosmic microwave background anisotropies and the large-scale structures we observe today will carry, therefore, an imprint of those primordial quantum fluctuations. Now, I claim that quantization of the geometry, although perhaps only a semi-classical one, is part of the game explaining the large-scale structure of the universe. This, I claim, is already true for the already observed scalar perturbations. Why? Because you cannot attribute this perturbation just to matter and not to the geometry, since the separation between matter and metric perturbations is well known to be a gauge-dependent concept. Of course, if primordial gravitational waves will be detected in the CMB via the B mode of polarization, then quantization of the tensor field, of the gravitational field, will be completely unavoidable. The second reason why I believe cosmology needs quantum mechanics is that inflation cools down the universe to practically zero temperature, because it's an adiabatic expansion and this cools the universe. So how can one generate a hot universe after inflation? You need that because if you don't, there is no cosmic microwave background, no Big Bang nucleosynthesis, and many other things. So we know for sure that there has been a Big Bang, a hot Big Bang. However, a note that after inflation, the universe is still expanding. So it has to expand and warm up. And that's where the second intervention of quantum mechanics intervenes, through the so-called reheating mechanism, which is a non-adiabatic conversion of potential energy into a hot thermal soup of elementary particles. This brings me to the second reflection, that in inflation, reheating replaces the old hot Big Bang. But of course, it has no associated singularity. There is nothing infinite at reheating. In fact, if any, it's difficult to get enough high at a reheating temperature. And it's certainly not the beginning of time, since it comes at the end of inflation. In fact, this is an often shown picture. I forgot now the author of this picture, but it's recent. And you see it has a Big Bang followed by inflation. And what I claim is that the new Big Bang is here and not here. Here there should be a big question mark instead of Big Bang. In fact, in inflationary cosmology, we have to distinguish a physical non-singular Big Bang at the end of inflation with its measurable relics, CMB, Big Bang nucleosynthesis, from a theoretical, maybe singular, maybe not, Big Bang, or maybe a regular big bounce, who knows, which may have preceded inflation without leaving relics, or maybe leaving relics. But this is completely hypothetical. In any case, the Big Bang we know something about has nothing to do with the beginning of time. And as understanding the latter issue of the beginning of time requires a quantum theory of gravity, because quantum mechanics is already very active during inflation and even more before. So, but now let's go back to the standard model of nature. I want to remind you of the huge role of symmetries in constructing this standard model. This is well known, appreciated, but I would like to distinguish two kinds of symmetries. There are global symmetries of the kind of flavor SU3, CP, chiral symmetry, together with their explicit or spontaneous breaking. And I don't have much to say about that. It's pretty straightforward. But then there are the local symmetries, like gauge invariance and general covariance, on which, as I emphasized, the whole standard model is built. Now, local symmetries are special. In fact, according to many, for instance, Nati, Seiberg is very vocal about that. They are not real symmetries. They are an expression of redundancy. A local symmetry is so big that it can be used to gauge away complete degrees of freedom. Examples: a massless spin 1 particle, we know very well, has 2 physical polarizations, while a massive one has 3. Now, gauge invariance allows to remove the unphysical polarizations of such a spin 1 massless particle. And analogously, a massless spin 2 particle has 2 physical polarizations, while a massive one has 5, 2j plus 1. And general covariance allows to remove the unphysical polarizations of the spin 2 massless particle. Now, I should also remind you that some 50 years ago, there was a crucial breakthrough that also local symmetries, like global symmetry, can and do have different realizations. There we talk about a Coulomb phase in which these massless particles are really there in the spectrum, a photon or a graviton, which we haven't seen yet, but theorists believe it's there. Or you can have a broad-angled Higgs phase, which is what is realized in weak interactions. Sorry, the Coulomb phase, of course, is realized in electromagnetism and gravity. The Higgs or broad-angular Higgs phase is realized in the weak interactions, and of course doesn't violate the idea that the gauge symmetry removes degrees of freedom, because it uses an extra degrees of freedom, a scalar particle, which is eaten up, as we say, and so the number of degrees of freedom is nicely confirmed. And finally, there is a possibility of a confining phase, which is the one which is realized in the strong interaction. So interestingly enough, all these different realizations of gauge symmetries do exist in nature. Now, so I'm making two more reflections related to actually the previous point, that nature appears to like spin one massless particle, and I'm saying that's why it is partly described by a gauge theory. And since nature also appears to like spin two massless particle, this is why it's partly described by general relativity. So I would like to turn things around and say that it is the very existence of massless spinning particles which forces us into playing the game of gauge invariance and general covariance. Now, there are, of course, many puzzles and conceptual problems. Fortunately, especially for the young generations, there are still many such puzzles and conceptual problems. You have plenty of things to work on. I don't want to spend too much time, but here is a partial list of particle physics puzzles. You can go through it quickly. In particular, I would like to underline that perhaps there are indications of some new physics in B decays and in the anomalous magnetic moment of the muon. But there are many mysteries like why three families, why we have such an enormous hierarchy of fermion masses, can we understand the mixings in the quark and lepton sectors, and why the neutrino sectors is so different, and so on and so forth. And we can go on with a similar list in gravitation and cosmology. There, perhaps the biggest puzzles is what is dark matter, what is dark energy, why is omega lambda the fraction of energy in vacuum energy of order 1 today, what is the origin of the matter-antimatter asymmetry, and so on. And I would say that there are not so many clues about these puzzles from presently accessible length or energy scales. Perhaps primordial cosmology can give us some more hints. Now, so instead of dwelling into these particular problems, let me stress some more general and perhaps more conceptual problems. As you know, quantum mechanics was introduced in 1900 to solve a UV problem, ultraviolet problem in black body radiation. It works fine in non-relativistic quantum mechanics. However, relativistic quantum mechanics, also known as quantum field theory, reintroduces a UV problem. The reason are this virtual pair creation, which are very good on one sense, but they lead to infinities, since virtual particles of arbitrarily high energy are too copiously produced in any local quantum field theory, at least in 3+1 space-time dimensions. Now, there is a recipe called renormalization, which handles these UV infinities, in particular of gauge theories, and gives a partially predictive theory, which is the standard model. Put it differently, our ignorance about short distances can be lumped in a finite number of parameters that cannot be computed, cannot be predicted, have to be taken from experiments. But the rest is in principle calculable and predictable. Now, the attempts to do the same for general relativity have failed so far, since the gravitational interaction grows with energy. So this copious production of virtual energetic particle is enhanced in a gravitational theory. And then the price of UV ignorance becomes infinite. Namely, you have to fix an infinite number of parameters from experimental data. And I should stress that the same would be true had we attempted to quantize Fermi's theory of weak interactions. To my mind, the only way to make sense of quantum gravity is to soften the theory below a certain length scale, let's say capital L, which has to be somewhat larger than the Planck length. That's where big quantum gravity effects come in. Now, and then therefore, like Fermi's theory with respect to the standard model, general relativity would then be just a large distance approximation to a better theory. Another question that I'm asking is, does nature know how to renormalize? And my answer is no. I mean, nature does not need to renormalize, because nature, unlike us, cannot be ignorant about the UV. She knows what happens at all scales. Now, this brings me to the subject of the missing quantum corrections. So quantum corrections can be good or can be bad. Most radiative corrections, what I would call the good ones, have been seen in precision experiments, as I said right at the beginning of my talk. For instance, the running of gauge couplings, scaling violations, some welcome anomalies which upset some global symmetries that we do not see in nature. The fact that you produce through loops for effective four Fermi interactions, which are very nicely described in a neutral Keown system, the quantum fluctuations during inflation. However, there are a fewer bad quantum corrections which have not been seen. And these are basically the corrections to the Higgs mass, the famous hierarchy problem, and the corrections to the vacuum energy, if you want, to the cosmological constant, which may be really a huge number of off. Now, from the point of view of an effective low energy theory, what we have seen are the expected quantum corrections to what are called technically marginal and irrelevant operators, and we have not seen those to relevant or low dimensional operators. Now, we know that quantum corrections to relevant operators, relevant in the infrared, the most important operators in the infrared, are sensitive to the ultraviolet physics. In the sense that, for instance, these quantum corrections diverge as powers of the ultraviolet cutoff. This is an indication they are extremely sensitive to what happens in the ultraviolet. So this may be the fact that we don't see these corrections to relevant operators may be telling us once more that the standard model and general relativity are not the full story. Now, I remember when I was young, in the mid-60s, Gell-Mann used to say strong interactions only read books in free field theory, because the quark model worked very well as if quarks were free, and yet nobody had seen a quark. But then came QCD, and it showed us with asymptotic freedom could explain why strong interactions read only those books. And we can paraphrase Gell-Mann today by saying, perhaps, that nature only reads books in dimensional regularization. In dimensional regularization, you throw away quadratic divergences and things like this. So nature only knows about the logarithmic divergences that we observe. So what reflection number 6, what we want is an intelligent ultraviolet completion of the theory. We'll need some understanding of ultraviolet physics such that it gives for us what we want, that reads the right books. So the last subject of this talk is whether that ultraviolet completion could be quantum string theory. And there are two quantum miracles that speak in favor. I stress very much the word quantum, as you will see in a moment. There is quantum string magic number 1, which is having angular momentum without having a mass. Namely, quantum strings can have up to 2 units of angular momentum without gaining any mass. This is classically impossible. You can easily find out. And however, it's not only possible, it is needed at the quantum level. This, if you want, was the famous Virasoro breakthrough in 1969. So I indicated here the classical inequality between mass and angular momentum in classical string theory. T is the classical string tension, which has a quantum corrections, and that quantum corrections allows to have angular momenta up to 2 units of h bar without having any mass. And as I said, it's not only a possibility, it's a necessity of the old string, of the old and new string. So this is just to illustrate in a slide what I meant. You see, classical string and quantum strings are not very different if you go to large angular momentum or to large mass. They resemble each other very closely. But if you zoom in this region of small mass and small angular momentum, there is a big difference. You see here, the straight lines start from the origin. Here they don't, and they allow massless particles of spin 1 and 2. And in particular, I would like to emphasize that classical string theory, namely this one, has nothing to do with classical field theory because it has no long-range force, no Coulomb law or Newton law. Now, the second quantum string magic is the appearance of a fundamental length scale, which is not there again in the classical theory, and that comes from quantization. This fundamental quantum length of string theory is related to the string tension through the Planck constant, and it's quite analogous to the Planck length, which is analogously given in terms of the Newton constant. And in fact, in string theory, we believe that the product of the Newton constant and of the string tension is something related to an observable, which is the fine structure constant or the grand unified structure constant. And this fundamental string length enters quantum string theory in many crucial ways. It is the characteristic size of the lightest strings. Of course, you can take very highly excited strings, which are much, much bigger than L string. It's at the basis of T-duality, mirror symmetry. It's related to the maximal temperature of string theory. And most important is the physical reason behind the good ultraviolet behavior of string theory, which doesn't have these infinities. Now, okay, this is an illustration. I mean, thanks to this fundamental length scale, the point-like interactions of field theory become smeared over regions of order L string in string theory. So to summarize, quantum string theory appears to have answered our two questions. Why does nature like spin 1 massless particle, and why does nature like spin 2 massless particles? Simply because they are unavoidable in a consistent theory of quantum strings. So this explains why it is well described by gauge theories and general relativity. So, and this particular property of string theory, together with the smearing of interactions, leads to a unified and finite theory of elementary particles and of their gauge and gravitational interactions, which is not just compatible with quantum mechanics, but it is based on quantum mechanics, because without the quantum mechanics of strings, you would not get all these beautiful results. And I should stress that it is through the first quantization of the string, then the second quantization, if you want, the field theoretical second quantization is ultraviolet finite, which I find very amusing. Now, however, having a UV finite theory does not mean absence of radiative corrections. Of course, we need the good ones, so better not. So the only thing is that now the radiative corrections are finite, in principle calculable. You are not allowed to play games, renormalize, or put infinities under the rug. So the question that comes is, does quantum string theory read the right books in the language of Gell-Mann, namely the absence of radiative corrections to relevant operators? Well, the answer is that all consistent quantum string theories are supersymmetric, as far as we know, and as such, they do satisfy that requirement, because we know that with exact supersymmetry, you don't generate either a cosmological constant or a Higgs, a large Higgs mass renormalization. But this is true in perturbation theory, and at that level, supersymmetry is unbroken, and we know that supersymmetry cannot be unbroken in the real world. So the next question is, can quantum string theory provide some mechanism of spontaneous supersymmetry breaking which preserves that particular feature of its perturbation theory? And the answer lies in the deep UV details. Now, could that be a selection principle for acceptable string theories? String theory has many vacua, so-called vacua. Maybe in some of those vacua, this happens. Or perhaps this is a sign of some subtle infrared ultraviolet connection or mixing. People, even at the string conference last week, were talking about things like those. Otherwise, we will be forced to play perhaps an anthropic game based on the huge landscape of string vacua, namely the fact that there are many solutions, and we'll have to play an anthropic game to select the good ones. But this possibility rests on the idea that we can find among all these string vacua at least one that resembles the real world. And I think we have not succeeded yet in doing that. This is indeed the very non-trivial string phenomenology program. And obstacles in that direction come from two perhaps less desirable quantum string theory miracles, which will bring me soon to the end of the talk. One is that quantum strings don't like 3+1 dimensional space-time. While classical thing can move in any ambient space-time, flat, curved, with an arbitrary number of dimensions, quantum strings require suitable space-times, or more generally, background, in order to avoid some little anomalies. In fact, in the case of weakly coupled superstring theories, space-time, if it's nearly flat, must have 9 space and 1 time dimensions. And in order to reconcile this with observation, we have to assume that the extra dimensions of space are compact and small, for instance, a 6 torus of radius of the order, say, of the string length parameter. So quantum mechanics pushes string theory into a Kaluza-Klein type scenario, to which it adds many interesting twists, such as T-duality, but I have no time to talk about that. And the other thing is that there are massless light scalar fields, which I like to call Achilles heel of quantum string theory. I told you already that there are very welcome spinning massless strings. Unfortunately, there are also scalar fields, which are massless. And this has to do with the fact that the usual quantum field theory parameters are replaced in string theory by typically scalar fields whose values provide the parameter, or if you want, the constants of nature. Are they dynamically determined? Well, in perturbation theory, most of them are not, because the associated scalar fields, called also moduli, are strictly massless. And so there is no potential that fixes their value. Now, if they remain massless, even non-perturbatively, then quantum string theory is very likely falsified by the fact that it predicts additional long-range forces that we don't observe. So this is the so-called moduli stabilization problem in string theory. It's one of the toughest and most interesting problems. On the other hand, if these moduli, the scalar fields, do acquire a mass and therefore a potential, then their vacuum expectation values will be fixed, or at least will take only discrete value, and this will in turn fix the standard model's constant. For instance, the fine structure constant, or the ratio of the proton mass to the Planck mass, will be predicted. That would be, of course, fantastic. But I want to stress, this looks like a win-win, lose-lose game. Either you don't predict, and on top of that, you have unseen long-range forces, or you win on both sides. So while today these constants look to be space-time independent, their variations may have played a role in early cosmology. So this is an active field of experimental and theoretical research. And I want to stress that there is no need for Planck scale experiments for testing string theory. And this, by the way, was also true for the old hadronic string. In fact, perturbative quantum string theory is already ruled out because of these scalars and these extra forces, but so is QCD. If you work at perturbatively, there is no confinement and you predict to see quarks. These are, for instance, some constraints on the string dilaton's mass, since we know its coupling to a large extent. We also know that it better have a mass corresponding to a range below 10 to the minus 4 meters. So I come to the summary. So what I tried to convey with you is the following, that our present standard model of nature is deceptively simple and successful. Its basic underlying principles, which is gauge invariance and general covariance, can be reduced to the existence of massless spin 1 and spin 2 particles. On the other hand, the devil, as usual, is in the details. For the standard model of elementary particles in the matter content, the Yukawa couplings, the Higgs potential, and so on. And for gravity and cosmology, the existence of dark matter, dark energy, this mysterious inflaton. Quantization of both standard models looks to me more than ever a must. Quantum mechanics in particular is crucial for modern cosmology, where the Big Bang has to be redefined. And quantum mechanics, unfortunately, brings in problem with its infamous UV divergences and its bad radiative corrections. So an intelligent UV completion appears to be needed. Quantum string theory with its magic could be such a sought-for completion, but quantum string theory has been often emphasized is a package. You just can't use what you like about it and throw all the rest. Quantum string theory comes already equipped with supersymmetry, but also with extra dimensions, with dangerous massless scalars, with a whole landscape of possible vacua. It is already ruled out at the perturbative level, but as I just said, so is also QCD. And I think it will take a while before we can solve quantum string theory non-perturbatively, and we have to do that both in curvature or derivatives and in the coupling, and find out whether it will survive or go down the drain like its hadronic predecessor, on which I was working 50 years ago. And not to repeat the old mistake, I would like to finish asking two questions. To which elementary particles should we apply string theory? And is it reasonable to assume no more substructures from where we are now till the string of Planck scale? And with that, I thank you for your attention.
Thank you very much, Gabriele, for the very nice talk, extremely clear and a very nice overview of both successes and puzzles, as you said in your abstract. So there were already some comments in the chat, in particular by Adi Armoni, but before letting him maybe comment, I wanted to use my prerogative as a chair and ask you a question. So it seems to me that, I mean, it's undeniable that quantum string theory captures some features of gravity. So at the very least, I think that one could say that it is a description of some consistent gravity theory at the quantum level, which is no small feat by itself. And then maybe you have to say, well, maybe it's only fine if you are interested in something that has supersymmetry or is in certain dimension. It might not really work when we really want to nail it down to 4 dimensions with the particle content of our universe and all the, the precise description of our physical universe. So is your gut feeling that going forward, we will have to use string theory as something that gives a flavor of what a quantum gravity theory can be and captures, at least some very essential features of it? Or we will actually be able eventually to nail it down and to resolve all these issues that you pointed out to us?
Well, thank you for the question. Well, in my opinion, first of all, string theory is a proof of, is an existence proof that it's possible to reconcile gravity and quantum mechanics. It's at least an example, at the price of softening the theory, okay? As I said, I made this analogy with the Fermi's theory of weak interactions, which I remind people, has 4 fermions interacting at the same point in space-time. That was replaced in the standard model by an interaction of 2 fermions with the intermediate vector boson, which then interacts with the other 2 fermions. So this displacement of this resolution of the 4 fermion vertex into 2 separated vertices is what made the standard model renormalizable, unlike the case for Fermi's theory. So in my opinion, this is the main lesson to be learned from string theory, that you need something that makes gravity less singular at short distances, and then there is no problem quantizing it. Now, because you see, you could say, well, why not invent some other scheme of quantizing gravity? For instance, you know, there are these nice attempts called loop quantum gravity, but in my opinion, they are not revolutionary enough, okay, in the sense that they do not really change the starting point, and they only try to address the question of how technically to quantize general relativity as such. And, you know, people tried indeed with Fermi's theory and never succeeded. But, okay, now to your question, I think I kind of gave a hint in the very last sentence of my talk, namely, I'm unconvinced that there is a desert between the energy scale which is accessible today and the string or Planck length scales, which is 20 orders of magnitude higher. Now, that would be unprecedented in the history of physics, that as you go down in scales by 20 orders of magnitude, you don't find anything, you know, any further structure. And who knows, maybe the fact that there are 3 families, maybe, you know, the unification perhaps of quarks and leptons and so on, calls for some substructure, at least of some of the particles. So in the old days, just to make more specific my point, we were trying to, we constructed a string theory for the pion or for the proton as if they were elementary. And we were wrong, because pions and protons are made of quarks and gluons. Now we say, okay, let's use string theory for the quarks and the gluons. Who knows, maybe the quarks themselves are made of something else. I don't know if this answers.
I will now leave the field for other colleagues to ask questions. Maybe if Adi wants to comment, since he wrote in the chat, if he's still connected, he can make his comment, which was about instances of non-supersymmetric string formulations. But
hello, Gabriele.
Oh yes, hi Adi.
How are you?
Fine.
There's no video, so you cannot see me. No, it was just a comment. There are few string theories without SUSY, and consistent string theories. So there is the so-called Sagnotti model, there is so-called Sugimoto model, and there are other models. And the interesting thing about the fact about these theories is that they seem to be consistent in the following sense. They are 10-dimensional, tachyon-free, unlike the bosonic string theory. And there is no fundamental problem with this. There are no Ramon tadpoles. So they look consistent. Of course, at the quantum level, there are potentials generated. So, and I don't remember whether the potentials push you to strong coupling or to weak coupling, whether G string equals 0 is stable or unstable. But what I wanted to say is that there is no requirement of SUSY, and which I think philosophically, first of all, philosophically, it tells us something, that quantum gravity is not tied with supersymmetry, right? So this is kind of a myth that string theories require supersymmetry and otherwise, or quantum gravity requires SUSY. I don't think that's correct. But the other thing is that then it's really interesting to, I mean, this thing that you said that only log survive, like in the dimensional regularization, so string theory also suggests that because string theory is SUSY. Well, it's interesting to see what happens to the cosmological constant
Mm-hmm.
these theories. Obviously, it is generated.
I see.
But like
at a big level, namely with the scale of the cutoff.
Yes. So
no, but it's
really
very interesting what you point out. I mean, as I said in answering the previous question, I think the essential thing is this extended nature of strings, which smears the interaction. Now, the fact that they come with supersymmetry, you know, it's an empirical observation, but as you point out, there are examples. And you say these are really non-supersymmetric.
Yeah.
It's not that supersymmetry is broken.
It's broken at the UV. Yeah.
It's really broken.
It's yes. So, well, it's kind of...
it's not spontaneously broken.
No, it's
really
not spontaneous. It's really broken. So, for example, in the Sagnotti model, it's based on a gauge group U32 with the antisymmetric tensor, two index fermions in the antisymmetric tensor, similar to the theories, the gauge theories we worked on together 15 years ago. In fact, the gravity dual of the gauge theories are the Sagnotti model. So I think they should be consistent.
Okay.
And but yet there is a cosmological constant. So it is interesting.
I think perhaps Ivano Basile has another comment, I think on the same. So let's see if Ivano wants to add something.
Yeah, yes. Hi, thank you. And thank you, Gabriele, for the very nice talk. I just wanted to add that, you know, regarding how supersymmetry is broken at the string scale in these models, in particular in the Sugimoto model, as Adi mentioned, it's not completely clear what kind of breaking it is, but it seems to point to a spontaneous breaking of some kind, because in the massless spectrum, there is a Goldstone fermion. But one would expect a sort of super Higgs mechanism, right? Because there's
a gravitino, a massive gravitino.
Exactly, but it's not, the details have not been worked out, because it appears that there is a mismatch in degrees of freedom in 10 dimensions. But maybe it works in a lower dimensional vacuum, because the Minkowski background that one starts from when studying these models in string perturbation theory is not an actual stable background. But it turns out that you can build lower dimensional backgrounds. So it's a long story, but to cut it short, so there's still lots to be found out in these models to be understood. But a review is coming actually tomorrow on the archive if anyone is interested.
Okay, thank you.
Thanks, Alessandro, for the...
That's excellent timing then, with the review coming out. And now, these were very interesting questions, maybe more for the experts, but I encourage also people that are not strictly experts to ask questions.
This was not really a talk meant for experts, as I said at the beginning.
And I think we have a couple. We have Zurab Veneziani, and after that we will have Gian Giudice, but let's start with Zurab.
Hello, Gabriele. It was a very nice talk. Thank you.
Thank you.
Very inspiring, actually. About your recipe, about nature likes dimensional regularization only for marginal operators. It would be very nice, but in the context of grand unification, which you mentioned also as a part of string theory, or perhaps, actually this hierarchy problem is related with marginal operators between two Higgs fields. One breaks SU5 and another breaks, and so it's reduced to that question, right? So it cannot work so easily in this context if there are some other scales, physical.
You mean that even in the presence of only logarithmic divergences, you still have
it is a
hierarchy problem
between two normal Higgses and two SU5 Higgses, which is a marginal operator.
Okay. It's not a question of masses, mass term turning negative.
Mass term appears when you substitute one vacuum expectation value, big one, in this quartic term, and this quartic term always appears from radiative corrections, if you like. You cannot suppress it. And in this case, I think supersymmetry only can help, nothing else.
I see. Okay. Well, thank you. Nice point.
Thank you.
And I think that we have Gian Giudice next.
Hello.
Hi, John.
Ciao, Gabriele. Thank you very much for the beautiful talk and the inspiring comments. Let me ask you one question. When you were discussing gravity, you said that we could live with classical gravity if it weren't for cosmology. But let me ask you about black holes. So don't you think that when we have black holes, we need to introduce quantum mechanics in gravity? And also related question, don't you think that one of the aspects, important aspects of string theory is its ability of to calculate the entropy of the black holes?
Yeah, good, very, very good questions. I mean, concerning the first question, yes, indeed, I did not mention quantum mechanics when I was talking about black holes. I would say that well, in my opinion, the only reason why I think you're right in a sense that quantum mechanics is also important for the black holes, I think is the singularity problem. I mean, in principle, the existence of classical solutions, you don't need, say, quantum mechanics to explain the merger of two black holes. On the other hand, if you want to describe the interior of a black hole, and if you're not happy with the fact that there is a singularity inside, then you better use something that removes the singularity. Here, I'm expressing my own viewpoint, which probably is not the majority viewpoint. I believe that also for this information paradox, when you apply quantum mechanics to the physics of black holes, even for that problem, I think the singularity question is relevant. I mean, because how to describe the interior of a black hole, you may need quantum mechanics. Then of course you are completely right about the interpretation of the microscopic interpretation of black hole entropy in string theory is of course one of the big successes, although it has been done only for some particular black holes. But okay, so if you say once you accept the idea that there is quantum mechanics also in gravity, then of course you have to draw all its consequences, including the fact that black holes have entropy. The entropy of a black hole contains the Planck constant through the Planck length, and therefore this calls from a statistical mechanics interpretation, and then you have the question of reconciling the information, with a thermal radiation a la Hawking and so on. So these are all very nice, beautiful problems that emerge. So, but okay, the way I was presenting it is that, at first sight you say, well, big black holes, who cares about quantum mechanics? But sooner or later, quantum mechanics hits you also in gravity. It hits you because, for instance, of the Big Bang singularity, and it hits you equally well because of the black hole singularity. So at that point, you give room to quantum effects, and then all these other puzzles pop out. And then I think you have to answer those questions within a consistent theory of quantum gravity, for instance, with string theory. So I basically fully agree with you.
So in the meantime, we had a couple more questions. So we have David and then Subir. Let's start from David.
So thank you very much for this encouraging account of the 50 years that I've been involved in particle physics. For the last 20 of those, some very good friends of mine had a metaphysical argument that the scale of supersymmetry breaking should be comparable to that of the Large Hadron Collider. Mm-hmm. That has not yet turned out to be the case. I mean, I regarded that argument as metaphysical because I work in perturbative quantum renormalizable theories, and you can't fine-tune infinity. But they really firmly believed in that. Do you have any metaphysical hold on what the scale of supersymmetry breaking might be?
No, I don't like metaphysics. And I remember that, you know, when I was teaching at the Collège de France, the last few years I was teaching about supersymmetry, and you know, at the risk of making enemies in the particle physics community, I was saying, well, I would love to see supersymmetry, you know, at the LHC, but if I should bet my money on it, I would rather bet that you won't find it. Why? Because of the reason I explained, that the standard model looked so beautifully well that, you know, it was quite strange to expect that no virtual effects from supersymmetric particles would show up. Furthermore, you know, the standard model has some beautiful features like automatic conservation laws for individual flavors and so on and so forth, which, you know, they're not so automatic in supersymmetric theories. So at this point, I have no guess, and in my opinion, the strongest arguments in favor of supersymmetry are related to this cancellations of these bad divergences. However, my hope is that, you know, you may find a way to break supersymmetry and still keep these cancellations. You see, let's put it this way. For instance, in a superstring theory, you have an infinite tower of bosons and an infinite towers of fermions. And of course, as long as you are completely supersymmetric, you can compute a radiative correction, say, to the vacuum energy, and you will find zero because there is a precise cancellation between level by level between the fermions and the bosons. But it seems to me that you have an infinite amount of freedom of changing a little bit the ultraviolet and still keeping this cancellation manifest. So, but you need some intelligent way of doing it. And I think nobody has found a real intelligent way. So this is to say that it could be that the supersymmetry works, but, you know, it doesn't have to work at a lower energy scale. That's all I can say at the moment. No, I have no particular inspiration about when, at which scales you should expect to find it, indeed.
Thank you.
So now we have Subir, and then after a question in chat from Lorenzo Maccone. Subir, please.
Oh, hello, Gabriele. Greetings from
hi.
Oxford. So some of us are watching your talk together, and I have a question from our alumnus, James Dodd, who worked on the Veneziano dual resonance model in the late 60s.
Wow.
but now he's asking a more up-to-date question. He's asking, must a theory show that the cosmological constant is 0, which I would slightly reword as follows. Is de Sitter space forbidden by considerations of the S matrix? There is no future infinity. Hence, as you know, this is a long-standing question, which has recently been revived by, for example, Giadwali and others. What is your view on this, please?
Well, that's a rather technical question, and I don't think I have very much intelligence to say. However, there's also claims that de Sitter is not in the landscape. You know, there is this idea of swampland versus landscape. And I think there are statements that, in fact, string theory, you know, doesn't like to have a purely de Sitter vacuum. Indeed, my preference for explaining the acceleration would be that there is still some field which has not relaxed to its true vacuum, and there is still some residual potential energy stored in that light field. Now, of course, this is easy to say, but not so easy to show that it's consistent, because this field has to be very light, and again, it can produce long-range forces, and you have to cope with that too. But for instance, if it's a pseudo-scalar, that could be perhaps a viable alternative. So if you really want to know, my true feeling is that I would rather believe in a vanishing true cosmological constant and in some other reasons for the acceleration. Now, I didn't think very hard about this point about defining asymptotic states and so on. And so on that, I have no particular opinion.
But thank you. I think you said your personal view is that you would rather see theory predict lambda of 0.
Yeah.
Thank you. Yeah, that's what. That's nice to hear.
Yeah. Somehow, I mean, sometimes I was expressing the following point of view, which I don't think people take it very seriously. That, well, we know, for instance, that superstring theory in 10 dimensions is consistent in flat space-time, right? And perhaps we should expect that even after you add all sorts of perturbative and non-perturbative effects, superstring theory is still, even after supersymmetry breaking, you know, all sorts of effects, that theory should still be consistent in flat space-time as an S matrix, as you say. But if you say that, you implicitly say that there should be a zero cosmological constant ground state, so that it keeps being so consistent in flat space-time. If you generate a cosmological constant, that means it's no longer consistent in flat space-time, that theory. Do you follow?
Yes, I got your argument. Thank you. And James is pleased to hear it too, I think. Yes. Thanks.
Thanks.
So I think we have one more question from Lorenzo Marcone. Please, Lorenzo.
Yeah, it's possibly a stupid question, because I'm, in contrast to the previous people, I'm not an expert, but I'm curious about whether string theory says something about the quantization of charge, of electric charge, and about the fact that the electric charge of leptons is the same, I mean, is consistent with that of hadrons.
Well,
I mean,
guess,
why the proton has the same charge as the electron?
Yeah. Well, you see, I mean, well, as I say, the new string theory doesn't consider the proton as a string, but maybe the quark as a string. So you can ask the same question, I guess. I mean, why the quark has charge, 2/3 minus 1/3. I mean, in principle, yes, string theory should explain charge quantization, which doesn't necessarily mean integer charges. And well, one thing which does it is, I guess, is the fact that, well, if you generate, there are two ways of generating gauge interactions in string theory. One is simply through massless spin-1 gauge bosons as open strings, okay? An open string can have a massless spin-1 particle. And the other way to generate gauge interactions is through the stringy version of the Kaluza-Klein mechanism. There, charge quantization is there because momenta in the compact directions are quantized by quantum mechanics. So this is already a very nice result of the old Kaluza-Klein scheme. So I guess that out of consistency, string theory must have charge quantization. And by the way, maybe this gives me an opportunity to stress why some of the symmetries of string theory really are quantum mechanical. A string, in particular a closed string, can move along a compact direction with quantized momentum, like a particle. However, a string can also wind up. A closed string can wind up n times around the compact direction. Now, it's interesting that the concept of winding is completely classical, right? I mean, this you can do in your, in your little lab. Okay, you wind up a rope and you wind it an even number of times, an integer number of times. On the other hand, the quantization of momentum is a quantum effect. Okay, it's quantized in units h bar divided by the radius. And it's very interesting that this T-duality of string theory, which gives a connection between compactification on large radii and compactification on small radii, is precisely a relation between winding and momentum, and heavily uses the fact that momentum is quantized. And of course, the associated charge is quantized. So, it's a symmetry which would not be there classically because the two concepts are on completely different grounds, but quantum mechanically, they get related to one another. So, but the short answer to your question, yes, I'm pretty sure that, when you do explicit compactifications in strings, in heterotic string theory, say on Calabi-Yau manifolds and so on, you then compute the spectrum of fermions and so on, and their charges under the gauge groups, you find this quantization. Presumably it's because the U1s are inside simple groups, non-abelian groups, and then probably the quantization of the U1 charge follows from the quantization of the non-abelian charge. But this I have to check.
Okay, thank you very much to all the people that intervened in the discussion. I think we had already quite a number of questions. So perhaps in view of time, I would thank again Gabriele.
And please send me comments or emails if you have other questions, or you find something clearly wrong with what was said.
Speaking of that, I think that on the GGI website, we will collect, so you can send also people that will listen to this talk, to the recording of this talk, they will have a chance to contact through the website the GGI. Will collect the questions and ask Gabriele if you can comment, and then we can also post on the website the Q&A for people that unfortunately maybe could not attend but will look at the recording. So that's good.
I would really appreciate it.
And once again, thank you, Gabriele. Thank you to everybody that took part in the talk and in the discussion. And please, Stefania, if you have some further announcement or comments.
No other announcement, just thanks again, Gabriele, for this very, very beautiful review and for the discussion. And please, Gabriele, send us your slides. We will post slides on our website. And an announcement for all the audience, we will have the last colloquium next Wednesday, and then we go for holidays and start again in September.
Okay. Thanks
Thank
a lot.
Thank you very much again, and have a nice evening, morning, or where you are. Bye.
To all of
Ciao
you.
a tutti.
Ciao.
Bye. Bye. Ciao. Ciao.